we'll do a brief walkthrough on this. So exam 3, you will get points back, okay? But you have to earn those points. Okay? That's something I'm big on. You have to earn and prove that you deserve the points back. So in preparation for next week, study, prepare for the final exam. You've got the practice of final. You will get exam 3 back on Thursday. Review exam 3, figure out what went wrong, fix those mistakes so that they don't happen again. Okay? Points back, you'll get half of the points missed or 15 points, whichever is fewer. Yeah. Office hours, extended office hours. Final exam prep, complete the practice final on what you think you know by this Friday. Get those answers submitted to me so that you can figure out if you actually know what you think you know or if something else is going on. Okay? And then the follow-up, finding 5 questions for anything that you think is wrong. Okay? Extra credit, the SECT surveys you should be seeing in email. You should be completing 2 of them. Okay? One for the chem lecture, one for the English lecture. You will also see one for the chem lab. You're not getting extra credit for that one. I would encourage you to complete it, but that's about it. Which then takes us into the leftover material for our last unit. Okay? Which I personally find a lot of fun and kind of exciting. And most people are so overwhelmed with all the math that they've had to do that you kind of zone out. Okay? One kind of good thing about Unit 4, how much math are we going to do? Virtually nothing. Okay? It's all conceptually based. Okay? And it's all conceptually based off of stuff that we've already talked about in the semester. We just start refining it and looking at independent applications. Okay? Where it starts, okay, is looking at our forces. Okay? In theory, you already watched a video that discussed what all of these forces were, right? Because you all answered true on that multiple choice on the exam saying that you were going to watch it. So you watched it. Okay? I found the success rate with that question is not very good. Okay? But we should have all watched it. Okay? Ultimately, the big thing that should have come out of that video is to get to the forces, you have to know what?
The types of bonds.
You would have to know the types of bonds. When we're talking about chemistry, chemistry as an entire field is really focused really on one thing. What is the attraction between 2 atoms? Right? That's it. Everything we do is how do I define or look at or evaluate that attraction? Okay? Sometimes it turns into quantifying it, dealing with conversions. Well, what was the mass of this one versus the mass of this one? Okay? How much of the new thing could I make? Okay? But ultimately, it zeroes in on just what is that attraction, and now how do I label all of those independent pieces? Okay? That attraction is really just a force. That force is a scale that ranges from really, really strong to really, really weak. Okay? Kind of like the rainbow. Okay? At one end, we've got
Scales.
red, and at the other end, we would have violet. Right? And just like within the rainbow, our scale of those forces or those attractions, okay, change. But when we look through the rainbow, it doesn't go red to orange to yellow to green to blue to indigo to violet. Well, wasn't that exactly what it was? So it's perfectly red to perfectly orange? No, there's a spectrum. It slowly shifts from one color to the next. When we've memorized the colors of the rainbow, we're really only putting human inventions on those individual places and trying to simplify it. The same thing happens with our forces. So when we look at our entire spectrum of forces, the first division that we do is we say, well, these forces are so strong that those 2 atoms are physically connected to each other. Right? And because it's a chemistry class, we actually don't say physically connected. We say chemically connected. They are now chemically connected to each other, and so I'm going to call the chemical connection what? A bond. Right? What would those bonds be?
Ionic, covalent, and then
How do we know we have each of those types? Because we're saying any two atoms, here's two atoms. How would I know which bond was there?
Isn't it ionic is metal and non-metal?
So in ionic, I would know I have one because it is a metal and a non-metal. Is that always true?
Yes. Should be.
What kind of bond is between the hydrogen and the chlorine? What is that?
There's a hydrogen.
A hydrogen bond is going to be a problem because if we look at our bond list that you just told me, it was ionic, polar covalent, and non-polar covalent. We said nothing about hydrogen bonding, okay? Which is a giant issue with this. Hydrogen bonding is not a bond. It is a force. So what is the bond connecting NH4 to Cl? What is NH4? Ammonium, kind of okay because I didn't ask you to memorize that one. Cl, chloride. What is the bond connecting those two pieces?
I don't actually know, but I'm just going to guess it's ionic.
Why are you going to guess it's ionic?
Because you wrote it under ionic.
I wrote it under ionic. That's an interesting hint. Not only that, what color did I choose to represent the compound? The same color as the ionic. So why is NH4Cl an ionic bond?
Is it because ammonium itself isn't covalent?
What is ammonium?
That's a good question.
Okay, so ammonium might be hard, so let's shift to the Cl. What is chloride?
Chlorine.
It is a nonmetal. Keep going. What would the symbol be for chloride?
Is it a gas?
I just said the symbol for chloride. So I don't care about its phase. Like, it's just Cl, dude. No. No, it is not. Cl2 would be diatomic chlorine. This is not chlorine, this is chloride. So we know it is different. We know that that Cl is Cl minus. How do I know it's supposed to be minus? How do I know I'm referencing the minus thing and not Cl2? When we look at the ending of the name, when I look at nomenclature, it is chloride with a D. That D says that what I am looking at is not elemental chlorine or even a chlorine atom. I'm looking at a charged chlorine, which would thereby make it what? A -1? Yeah. What's the name for that -1 species? And don't tell me chloride. An anion. An an what? What kind of bond might we expect to see between chloride and something else? An ionic bond. Why? Because it's a freaking ion. Right? It's literally part of the name. But you might be, well, how would I know? A metal and chloride or chlorine would be an ionic compound. Well, why is it an ionic compound? Well, metals have very low electronegativities and nonmetals have very high electronegativities. So ultimately the definition of ionic and polar covalent and nonpolar covalent has to do with differences in electronegativity. What is the electronegativity of iron?
We weren't supposed to memorize it.
We were not supposed to memorize that. In fact, if you ask anybody in this room the electronegativity of iron, literally anybody, how many people will know that answer?
No. Or you.
No one. I don't know that answer.
I gave it a
Okay?
try.
Which is a good idea. You might just assume, oh, he's a chemist, he knows stuff. No, what I've learned is to not memorize things. That is something I don't need to memorize. Why do I not need to memorize it? Because when it comes to an ionic compound, I know iron with chloride will be an ionic compound because what did I memorize? That a metal and a nonmetal is an ionic compound. So I memorized the exact same thing you did. Well, how do I also know that ammonium chloride is an ionic compound?
Because we know chlorine is anion.
Because we know what?
Chloride.
Chloride is an
Ion.
ion. That's why I know it's an ionic compound. So if I have some basic structural elements of nomenclature, I can predict those bond types. The general trend, metal and nonmetal, is a phenomenal example. It's not perfect. Okay? It covers the majority of our ionic compounds. How would I know ammonium chloride is also ionic? Well, chloride is an anion, and ammonium is a polyatomic ion. Oh, it's an ionic thing. It's part of what it's classified as. Does that make sense? Okay, so metal and a nonmetal, phenomenal statement. That is absolutely good. Just recognize it has limitations. Okay, those limitations should be kind of obvious if you have some of that secondary knowledge. Okay, kind of a second example to go with this. Okay, when learning how to drive, my dad was complaining about a whole bunch of rules that he learned growing up for driving. Okay, and one of the rules that he was taught is that when you pull up to a stop sign, you have to wait for 5 cars to pass before you are allowed to go. What the hell? What kind of rule is that? Okay, well, the whole point of that rule is that if you wait for 5 cars, what has your car done? It's come to a complete stop, which is what you're supposed to do at a stop sign. Okay? But what if there's no cars?
You're stuck there, or
You're
piss off the person behind
stuck
you.
there forever. Okay? So the rule was designed to say, make sure you come to a complete stop. So they invented kind of an arbitrary system to force you to say, I need to come to a complete stop. 5 cars. What if there's just a constant line of cars moving with no break in it? Are you going to be able to wait for just 5 cars and then just go? Does the oncoming traffic know you waited for 5 cars? Okay.
Damn well should.
So what we have to do is think about our rules of thumb to adjust what is the underlying mechanism behind it. Why are we doing it? Waiting for 5 cars was to make sure you came to a complete stop. Okay? Metal and non-metal is because most of the time that works for us. But we do have to acknowledge there's some underlying things that might pop up. Kind of make sense?
Next
Okay.
time I'm on an accident scene, I'm going to ask the driver, did you wait for 5 cars? There's not. This ticket is from my staff.
So if you're on an accident scene, you may be dealing with someone with a head injury, so they probably won't remember it anyways.
Yeah, that's
I
true.
won't be dealing with it. I'll turn them over to fire and say, y'all
So, ionic metal and a nonmetal, ultimately an ionic compound, is one that has ions in it. Okay, which sounds kind of dumb, but that's really where it's coming from. Okay, or ultimately where it's coming from is that difference in electronegativity. Okay, polar covalent, nonpolar covalent.
So I remember in the video that the covalent is non-metal to non-metal. However, the nonpolar covalent generally deals with the same element.
So if we think through that, our covalent meant non-metal to non-metal. That's what we learned in nomenclature. Okay? So if we use non-metal to non-metal, we would be classifying HCl, 2 nonmetals, in the same category as, say, water's a bad example, as methane, which of course I wrote horribly. Okay. Do both of those have the same properties? If I threw HCl at you versus threw methane at you,
We're going to have different effects.
yeah, those are going to have pretty different effects. HCl is going to be,
Hydrochloric acid.
I'm melting. The methane's probably going to be,
Just gas.
Don't let me on fire.
yeah, don't light me on fire, and that's it. We have pretty drastically different properties between those. They're both still nonmetals. So we would need something to further refine the difference between those. That refining is where we're getting polar covalent versus nonpolar covalent. Okay? And what's happening there is, again, due to a difference in electronegativity. But since we don't want to memorize electronegativities, we need a rule of thumb to help us out. What is that rule of thumb?
Non-polar covalent are usually the
same to same. Okay? Non-polar covalent, there is no difference in electronegativity. When are you going to have no difference in electronegativity?
When you have two of the same elements.
Two of the exact same elements have the same electronegativity, which means the difference in it will be zero. Non-polar covalent. There's no polarity associated with it. There's no poles. That definition works. It's just insanely narrow. Okay? And because it is so narrow, it's not very applicable. Okay? And so ultimately what we did is broadened that definition to include one more little piece in our rule of thumb. The hydrogen to carbon bond. Okay? So what we would need to do is memorize that ionic is metal and nonmetal. Non-polar covalent is same element to same element, and hydrogen to carbon. Well, then what is polar covalent? Polar covalent then encompasses everything else. This allows us to quickly look at a compound, identify the bond types. Once we have the bond types, we can then do something about predicting the types of forces. Right? So how would I predict the forces? Well, which bond type is going to generate an ionic force? Why do you say ionic?
Because they're literally named the same thing.
They are literally named the same thing, yes. An ionic bond generates an ionic force. Okay? A nonpolar covalent bond will generate what type of force? It might be, well, it'll generate the nonpolar covalent force.
No,
It's the London dispersion force. What the hell's going on with that? Or even van der Waals. Why do we not name it something nice and obvious like we did with the ionic compound?
Because that guy said you're wrong.
In a nonpolar covalent compound, there is no polarity. There are no charges in the compound. If there are no charges, should it interact with anything else? No, the only reason we get, or the primary reason we get things to interact with each other is because of charge. When I build hydrogen, I have a proton. Does it just sit as a proton typically? No, what happens? It gets an electron. Why does it need an electron? To balance the charge. Our basic building of elements is all about a balancing of charge. The same thing's happening on a molecular scale. We need to balance that charge out. If I have a nonpolar covalent compound, there is no charge. If there is no charge, should it ever react? Well, no. Which means what kind of attraction force would be between compounds that don't want to interact with each other? They wouldn't interact. They just wouldn't. It would be zero. There would be no force. Okay? That makes logical, conclusive sense. Turns out that that logical conclusion is false, okay, or wrong, okay, which means since they do interact, somebody else got to come in and say, you are wrong, your logic was false, this is how it actually works. And because of that, what happens? They get to name it. And in the process of naming it, that's where we sometimes see van der Waals forces. The guy that was primarily responsible for defining that attraction force. Okay? You can sometimes see it as London dispersion. I've got no explanation for where that comes from. You can also hear it referenced as induced dipole. We've come up with a multitude of different names to describe this. Ultimately, that force is exceptionally weak. Okay? And it comes from our nonpolar covalent, it's color code, from our nonpolar covalent compounds. Yes?
I thought you said in the Platon that for the London, that was where he was from or something like that. And it had to do with
I think I made that up.
And it had to do with the grid, didn't it?
I probably made that up. And by probably, I'm like 95% certain I completely and utterly made that up. Yeah. I do that sometimes. Sometimes. You just have to catch me in it. Okay?
So when I get my exam back and I look at my score, I'm like, you made that up.
Yeah. Yeah, absolutely. And everybody laughs, oh, haha, that's not. No, you absolutely should look at it and be like, did he just make that up? Did he just throw random numbers on there? And you should go back and look at your work and be like, no, actually, no, he wasn't lying about that one. I actually did do that wrong, or did that wrong. Okay, you should prove that to yourself and back that up. Because if you can't back that up, then you are accepting whatever's written on there, and it could very well be a mistake. You should be validating that. Okay, just like you should be validating whatever anything a teacher decides to throw at you, like London Bridge. Okay. Yeah. So polar covalent would then be everything else. Well, we got ionic covered in London dispersion, then polar covalent must be somehow responding to both of those. Okay? And we might say, well, what's going on with that weird definition again? Because dipole-dipole doesn't sound like polar covalent. Okay? Dipole-dipole is actually directly tied to polar covalent. Polar covalent means we take a polar covalent bond. There's a polar covalent bond. Oxygen to hydrogen. That's not nonpolar. That's not ionic. Okay, it is polar because oxygen is more electronegative than the hydrogen, which means where do those electrons go? They go towards the oxygen, which means the oxygen is now accepted electrons, making it partially negative because it's not a formal charge. It's not ionic. What happens to the hydrogen? Partially positive. Okay? So we have a bond now that has two aspects, a positive end and a negative end, kind of like a magnet, a north end and a south end, right? Except when we talk about magnets, we don't call them ends, do we? What do we call them? We call them poles. How many poles do we have? Two. Two pole just sounds weird. So we would call it a dipole. If I now look at how this bond interacts with another bond, I'd be looking at a dipole interacting with a dipole, and I get dipole-dipole. Literally, the name of the force between two polar covalent compounds has to do with the hyphen between dipole-dipole. That's really all we're talking about. Okay, when we reference the term dipole-dipole, it's the hyphen representing the connection between the two bonds. Okay, we just happen to call it dipole-dipole. Okay, that would be a more interesting one. That could be a dipole squared.
Dipole times 2.
Didipole.
Quad pole.
Quad pole would suggest you've got 4 poles, though, not 2 dipoles. So that one's got, because quadrupoles do exist. So we got to be careful with that one. Okay, so in any case, dipole-dipole. So we really end up with 3 primary classes: ionic, dipole-dipole, and London dispersion, tied back to those individual forces. Hydrogen bonding, I haven't explicitly stated yet. And you'll notice hydrogen bonding is indented. Why would the hydrogen bonding be indented?
Because there's an exception.
It's not so much an exception as in a further refinement of the forces. Okay? When we go through and look, we're getting, and I know I cut that word off. And I'm cutting that one off too. We really have those 3 classes. And hydrogen bonding is this subclass within there. Right? What is hydrogen bonding in reference to? When do I have hydrogen bonding?
Hydrogen is involved.
When hydrogen is involved.
The exception of hydrogen and carbon.
Is that dotted interaction up there hydrogen bonding? Right there, everybody see that? Is that hydrogen bonding? Because that matches Robbie's definition. It has hydrogen involved. No, that's not hydrogen bonding. Okay? We heard a different one, except when it was hydrogen and carbon. How about now? Now it's not hydrogen and carbon. So it was a nice attempt to refine. Is it hydrogen bonding now? Still no. Okay. Is it hydrogen bonding now? Can someone name that compound for me? Water. What is special about water? Particularly in reference to hydrogen bonding?
Two hydrogens bonded to an oxygen.
That's not hydrogen bonding. Water is our classic hydrogen bonding compound. Okay? And what it is referencing is that dotted line. When we look at the water molecule itself, the bonds within water, those are not hydrogen bonds. What are those bonds?
Oxygen bonds, because it's more much like.
Those aren't oxygen bonds either. Some people are like, well, I don't even know what bonds we have. Pretty sure you do, because we just spent 15 minutes listing off what the bonds are. What are our bonds?
We have
Polar covalent, ionic, and nonpolar covalent. What kind of bond do we have between oxygen and hydrogen? It is a polar covalent bond. It's not a metal and a nonmetal. It's not same to same. It's not hydrogen to carbon, which means it falls in the everything else. Those are polar covalent bonds. Everybody would like to call them hydrogen bonds because they have a hydrogen. You should not be doing that. Okay? And the reason why is because when you're saying it's a hydrogen bond, what you're trying to say is that there is a bond there that involves hydrogen. But when you say hydrogen bond, that statement immediately has the connotation of hydrogen bonding, which is not a bond between hydrogen and something else. The bond between hydrogen and something else would be ionic, polar covalent, nonpolar covalent. What?
The one you call like a hydrogen force or something.
What we are talking about with hydrogen bonding in quotes is not a bond. It is a force. It is an attraction between two molecules that are not sharing electrons. Okay? Which means when I'm talking about the hydrogen bonding interaction, I'm literally talking about that dotted line in between. There's a reason it's not shown as a solid, because what does a solid line mean? A chemical bond, which would mean ionic, polar covalent, or nonpolar covalent. We're showing it as a dotted line because it is not a formal bond. It is an interaction between those two separate molecules. It is technically an intermolecular reaction because it is now two separate molecules that are interacting with each other. Okay. Okay. Why do we need this extra concept of hydrogen bonding? We just said water was our primary example for hydrogen bonding. Why would I need to use hydrogen bonding as an extra thing? What's the liquid you used in all of your Gen Chem labs? You did not use hydrochloric acid as a liquid. Hydrochloric acid would be hydrogen chloride, and as a liquid you have to drop to negative 78 degrees.
Water, like it's the water.
You used water. So when you used hydrochloric acid, you used hydrochloric acid or hydrogen chloride dissolved in water. What was the liquid? Water was the liquid. We added something to it. So water is our primary liquid for all of our reactions. Why did we pick water? Safe is a possibility to it.
It's most common.
It's the most common thing. 70% of our planet, 80% of our planet is freaking water. Okay? Virtually all discoveries within chemistry are going to be based around the one thing that we all have access to, water. Okay? So we studied water a lot. We studied it so much and noted that when we moved to other substances, that those other substances didn't have the same properties as water, which meant we had to identify what that special property was in water. What was that special property? We decided to call it hydrogen bonding. Why did we not call it Bob? No idea. Bob is a better name than hydrogen bonding. What's the problem with calling it hydrogen bonding?
It doesn't bond.
It's not a bond. Okay? It is an attractive force between two molecules without an actual chemical bond. That is a huge, huge issue within this. Okay? How do I know I have the capability to make a hydrogen bonding interaction? What kind of bond was found in the molecules? A polar covalent bond. So I'm taking a polar covalent bond and a polar covalent bond, and I show them interacting with each other. What kind of force would that make? Polar covalent bond with a polar covalent bond would make what kind of force? A dipole-dipole. To have hydrogen bonding, one condition must be satisfied. What is that one condition? You must have a dipole-dipole force. No dipole-dipole force, no hydrogen bonding. If that was the only condition, wouldn't hydrogen bonding and dipole-dipole be the exact same? Yeah, they would. So there must be another condition. What is that other condition? One should be really blatantly slapping you in the face obvious.
You can't have hydrogen in carbon.
Too specific.
It can't be.
HCl. What is the attractive force in here? Are those dipoles? Is HCl a dipole and HCl a dipole?
Yes.
Shit, that was a bad example. Let me switch. Carbon and oxygen. Are those both dipoles? Yes, they're both polar covalent. Is the interaction between the chlorine and the carbon hydrogen bonding? No, why not? Let's try that again. Is the interaction between chlorine and carbon hydrogen bonding? No, why not? There's no hydrogen. What's one of our conditions? It must have hydrogen. I have to have a dipole-dipole force, and it must have hydrogen. Like I said, it was slapping you in the face. It was right there. You have to have hydrogen. Okay? The next part behind this becomes a little bit trickier. Not only do we have to have a hydrogen, but we must have a hydrogen, and we'll try and avoid ambiguous terms, chemically linked to what? You know one right out of the gate because what did we say water was the classic example of? Hydrogen bonding. Do we have a dipole in each of those? Do we have hydrogen in each of those? What must the hydrogen be chemically linked to if we know water is a hydrogen bonding compound?
The non-hydrogen element.
Use literally the specifics of water. Because if we run with the non-hydrogen element, we could do methane. Doesn't work. Oxygen. It must be chemically linked to oxygen.
That was cute, by the way. I still have it.
Okay? Is that it? Does it have to be chemically linked to oxygen? How do we know? Well, we go out into the world and we test a whole bunch of different substances with hydrogen chemically linked to a different atom that satisfy the dipole-dipole force, and we say, which of those generate this weirdly strong interaction? And we find out there's two other elements. What are those two other elements? Are you not having enough fun? Because I'm attempting to make some funny jokes. Fluorine. You can shake your head all you want. You got fluorine.
Is nitrogen?
Fluorine, oxygen, and nitrogen. Your hydrogen must be chemically linked to fluorine, oxygen, or nitrogen. If it is not chemically linked to one of those, okay, and we do not have a dipole-dipole force, it is not hydrogen bonding. Those two conditions must be satisfied. Okay? If we have a hydrogen chemically linked to fluorine, oxygen, or nitrogen, we have a dipole. We need to have a second dipole to generate a dipole-dipole force. Why fluorine, oxygen, and nitrogen? What do those three elements have in common? They are all diatomic, but so is chlorine, bromine, iodine. And those don't count.
They're in the same group.
Fluorine, oxygen, and nitrogen are not in the same group. They'd be in the same period. Okay, which is problematic because chemistry changes across the period. One of the properties that drives almost all of our chemical reactions is electronegativity. Fluorine, oxygen, and nitrogen are the first, second, and third most electronegative elements on the periodic table. By being the most electronegative, what are they doing to the electrons in the bond between the oxygen and the hydrogen, or the fluorine and the hydrogen? They are fully taking those electrons, okay, or taking most of them, which means what happens to the charge on the oxygen, fluorine, or nitrogen? It becomes very negative. The dipole generated in a hydrogen chemically linked to fluorine, oxygen, or nitrogen is so large that I'm generating an incredibly strong force between those individual compounds. That force is now so strong that I don't want to just call it a dipole-dipole. Okay? Who's the strongest person in this classroom? Just volunteer. I'm going to say James. Part of not military.
James too.
Yeah. James is the strongest person in this classroom. Okay? Does that make him the strongest person in the world?
Yes.
Okay? We have levels of strength. James may be the most strong in here. He may be the strongest dipole-dipole force. But if we throw him against the mountain, and I don't mean the physical object, the mountain, I mean like
I create the sequel to Mount Rushmore.
the weightlifter, the mountain from Game of Thrones and all, right? Okay? He's no mountain. Sorry, James. So the mountain would be a hydrogen bonding interaction. Incredibly strong. James is pretty dang strong, but he's not there. Sorry. Again. Okay? So what we're looking at is stages of those strengths. The interaction is so much stronger in the hydrogen bonding that we want to subcategorize it. We want to stand that out and put it as so important because it's such a strong interaction. Not only is it such a stronger interaction than a dipole-dipole, it also happens to be one of the most common interactions that we would ever encounter because hydrogen bonding happens in water, and water makes up 70 to 80% of what we deal with. So not only is it this extremely strong interaction, but it's also incredibly common. So we want to further accentuate it and set it off as its own category. That's why we end up with those categories. Okay? What the video walks through is how we could look at those and how we rank those to come up with the strengths. Where the video ends is looking at something like this. I believe it ends with this, which is looking at your spectrum of intermolecular attractions. Okay? And that's what's happening at the top. Okay? This is the interaction between any two atoms. I don't care where the atoms are, there's an interaction between them. What is that interaction? That goes from being incredibly strong on this end to incredibly weak over here. So the best way to think about this is not this big loop, okay, or not only is this big loop, but imagining this pulled straight out. It's a straight line spectrum all the way across. About halfway through, based off of how I've got it labeled, we've decided that that strength of interaction is strong enough that we're going to define it to be a bond. Okay? It's different enough to call it a bond. That interaction right at that threshold I'll call ionic. Why will I call it ionic? Because at that point I have yes, metal and a nonmetal. I have ions. Okay? As I continue to have those individual atoms share electrons with each other, I progressively become a stronger and stronger attraction between the atoms. So our nonpolar covalent bond is now the strongest attractive force between those two atoms. Okay? As I weaken that attraction, okay, either through changing the identity of the elements, okay, or through doing some other chemical properties, I'm shifting my way around the circle. Okay? Within each of those bonds and forces, we have subcategories. Why do we subcategorize it? Well, when you talk about the rainbow, what colors are in it? Okay, interesting. That's actually fun. That's not where I wanted you to go, but hey, you could say a lot. Okay, so when you're told to memorize the colors of the rainbow, your answer is a lot. Roy G. Biv. Why do we tell you to memorize Roy G. Biv and not just a lot? We could go through and assign specific colors. We can differentiate those. If we just say a lot, are we differentiating those? No, we haven't provided any structure behind it. The same thing's happening with our forces. We're providing a structure behind the differentiation of those interactions. Okay? Why is that structure important? Well, that structure becomes important because we're now talking about how those different things interact with each other. Well, why do I care about interactions? Well, do you care about your interactions with the rest of the world? Not really. So you don't have teachers. You don't have friends. You don't have colleagues online. You don't have parents, brothers, sisters, siblings. They're just people.
This man's got a point.
All of them are exactly the same. The interaction you have with your future spouse is the same interaction you have with me. You should be freaking out a little bit because I am.
You're showing
Okay? We differentiate those things. The same thing's happening with forces, and we can see that in how those interactions play out in the outside world. We can look at how they mix, their vapor pressures, right? Their phase transitions. We can define physical properties based off of these interactions. Okay? That's pretty freaking cool. Okay? And that's what this next section attempts to do, is it looks at some of those and says, well, why would we see this particular property for these compounds, for this structure? That's neat. Right? And that's where we'll pick up Thursday? Thank you. On Thursday. So you need to be able to identify bonds based on the atoms that you see. Once you know the bond, you can tell me what the force is. Once you know the force, you can rank them according to their strengths. That strength is ultimately dictating our physical properties. Right? This is multiple steps through. Just like dimensional analysis, we have to process our way through it. Okay? Except unlike dimensional analysis, what can you not rely on? Numbers to save you. And we're done.